energy in a solid. So you have one energy band in energy. So you have this range of energy here, okay, which is the first energy band. So the electron can take any energy in this range, followed by forbidden energy gap, okay, which is this gap here. So the electron cannot take any energy value here. Then comes another energy band, which is the first or the second. This should be second, right? This is the second energy band, right? Because the first, that one is the first, and this is the third energy band, right? So I got those wrong here. So this is the third energy band, right? Okay. Again, here you have forbidden energy range and allowed energy range here, right? So that's how we have bands, and that comes directly from quantum mechanics. So what I told you in this uh, brief uh, part, or in the past 30 minutes or so, that I looked qualitatively at bringing 10 to 22, 10 to 23 atoms in a solid. And then I told you about how electrons do not like to stay or sit in the same energy state. So that's why the energy states are spread out, forming a band. So we looked at that qualitatively. But then also, if we apply quantum mechanics and solve the Schrodinger equation accurately using quantum mechanics, we also immediately see that we come up with the same conclusion. Energy bands followed by forbidden energy gaps. Now, we have crystalline solids, okay? And we have our energies, okay? So what I'm going to do is, I'm going now to focus in the two topmost, the two upper bands, okay? Because all these bands are presumably filled with electrons, okay? And these two last bands are the last filled electrons with the highest energy in this crystal or solid, okay? So if you look at the two highest bands, let us look at different scenarios in these bands, okay? So let's look at this first scenario in this band, A. Let's assume that we're talking about the two top bands, right? So this is the lower one from the two top bands. Let's assume that it's completely full with electrons. So look, here I'm telling you it's completely full. I told you before it's one electron model which created the bands, right? Now I'm talking about full, as if I'm saying there are more electrons. So what I'm doing now is, okay, forget about the one electron. Now let us use the outcome of the one electron model, which is these bands. And now let us talk about a realistic solid. Let us have all our 10 to 22 electrons back and put them in these bands. And that is completely allowed. And that's what we exactly did in the case of atoms, right? We solved the atom's problem, the hydrogen atom, which has only one electron and one proton. And from that solution, we obtained the different energy shells. But then we said, okay, we use this simple atom and we produce the energy shells or the energy states. Let us now fill them for any other atom which has more than one electron, which has 3 electrons, which have 4 electrons, 10 electrons, 20 electrons, as we go through the periodic table. And remember, in each case, in each of these atoms, we also have Coulombic repulsion between electrons, which we ignored in solving for hydrogen because we only have one electron. But again, that model, of using the hydrogen model and filling up all the other atoms works very well. So we're going to do the same. We used a one electron model in the periodic potential. We produced bands from that model. Now we're going to talk about a realistic solid where we have these 10 to 22 electrons per cubic centimeter or even more. And then we're going to fill these bands with these electrons. Okay? And then we're going to distinguish between different solids. So let us take a situation where we start filling these bands. So this lower band is completely full. We're talking about the two upper bands. So this lower one is completely full. Then we have the energy gap, which is small, as you can see here. But then the top band is partially filled. So it's not completely full. There are so many energy states up here that are vacant, empty. So what happens is, if we apply an electric field, which is giving electrons energy to move, then these electrons can have more energy and go up in energy. So they have plenty of energy states empty to go up to. In other words, this material can accept energy from the electric field and therefore electrons move, or get kinetic energy, so they can move on. And so this is called metal, right? So what you have here is actually a metal, okay? So this is metal. Now, in contrast to this one here, again, the bottom band is completely full, but then the top band is completely empty. And then you have a range of energy which cannot be occupied by any electron. And this range of energy, Eg, is very, very large. So Eg is large. Okay? So now, if I apply an electric field, a potential if you like, electrons here will acquire energy. But they don't have any states to move into because all the states are full. So they would say, oh, I don't want this energy. I don't have any place to move. It's like a very, very large crowd in and blocked by a wall in front. And then somebody is pushing. No one wants to move. No one wants to take the energy and move because it's congested, so many people, and you don't have any place to move into, and therefore they don't want this energy. So this exactly happens to the electrons here. But what electrons here, in the bulk. But what about these electrons here at the top of the band? They can move on. They can accept the electric field or the potential and move on. But they are not willing to do that because they cannot move here. They are not allowed. This is not allowed energy states. They can only move all the way up here. But then they need huge energy, very large energy. So if you don't give them this huge energy, they are not going to accept any energy because they're not allowed to go into this energy gap. So they will tell you, no, thank you. We don't want any electric field energy. And therefore, we're not going to move because this energy barrier is so large and we cannot go through it. This is typically what an insulator is. Okay, so an insulator is a material with a completely filled band, second to the top, and a completely empty top band, and the separation in energy, the energy gap between the bottom and the top band is huge. So it needs a very, very large electric field to be able to conduct. Okay, so that's an insulator. But this is an interesting material now. It's like an insulator with a filled band here and an empty band up here. Okay, but then the band gap is small, which we call Eg. Eg is the band gap, right? So Eg is the magnitude is the band gap, and this band gap is the difference in energy between the two topmost bands. So the band gap is small. So what can happen is you can apply an electric field, an electron from here can actually jump up here, okay, and become conducting, take more energy and proceed. You don't even have to apply an electric field yet. All this picture is true at temperature T equals 0 Kelvin. This is the picture, of the bands and the energies. Now, if you increase the temperature, okay, maybe you give the electrons here enough energy even to make it up here, okay, and become field states in this empty band, just with increasing the temperature. And therefore, you have the same situation as that in the metal. This top band now has some electrons that are filling the bottom of this band. And so if you apply an electric field, then the electrons will respond and will therefore contribute to conduction at higher temperature. So this is an interesting material which you call semiconductor. A semiconductor is an insulator at T equals 0. Why are we saying insulator? Because this is empty and this is full. Just like an insulator here, this is empty, this is full. However, the difference with the semiconductor is if you increase the temperature a little bit, then you can energize some of the top electrons here, and they acquire enough energy to surmount the band gap and go to the empty band, and therefore become conducting. Now, that leads us to label these two bands according to conduction and non-conduction. So this bottom band is called the valence band, meaning that if we have electrons in this band, they cannot conduct. They have to go to the conduction band, which is the top band, because that's the band where they can actually find enough states, energy states, to move into and therefore conduct. So the bottom of the two top energy bands is called the valence band, and the top one is called the conduction band. So in a metal, you have a full valence band and a partially filled conduction band. In a semiconductor, you have a full valence band and a completely empty conduction band. And the band gap between the valence band and the conduction band is so huge, so large, so that you cannot get electrons excited by temperature from the valence band to the conduction band. However, in a semiconductor, you have the same picture as in an insulator. You have a full valence band at 0 Kelvin, at 0 temperature, and an empty conduction band, again at 0 temperature. But then you have a band gap, Eg, which is somewhat small, very much smaller than that in the insulator. And therefore, you can excite some of the electrons in the valence band thermally, and they can actually jump to the conduction band, and they can be available for conduction. Okay, so that's the idea of a valence band, conduction band, and that is how we differentiate between metals, insulators, and semiconductors. So that's exactly what's written here, is what I described in the previous picture. Now, these electrons that go to the conduction band are called conduction electrons or free electrons, free from the atoms, so they can move freely in the conduction band. They can respond to an applied electric field and move around, and they can respond to a voltage and move around and conduct. Therefore, they're called conduction electrons or free electrons. And they go to the conduction band. So here, they are referred to as free electrons. These are the electrons in the conduction band. Okay? So these free electrons exist in a metal. Okay, here they are. All these electrons in the conduction band are free electrons, and they can exist in the semiconductor because they can be excited thermally at higher temperature, but they do not exist in an insulator. So that is why the insulator does not conduct. Okay, so that's the picture. And again, I told you about the energy gap, which tells you how large the separation between the valence band and the conduction band, and we found out that is huge in an insulator, but reasonable and small in a semiconductor. Okay, and normally I told you the spread out of the band is of the order of 1 electron volt. So you see all these energy bands, the width of these energy bands is of the order of 1 electron volts. And you have something like 10 to 22, 10 to 23 levels, which are coming from the individual atoms within that band. Therefore, the separations between these states is of the order of 10 to minus 22 minus 23 electron volts. So that is practically zero. So that's why we show it as a continuous energy states, right, within the bands. So all these energy states within the bands are continuous. Here is just a table showing you the different energy gaps for different single crystals. Okay? So carbon, look, the energy gap is 5 to 6 electron volts. That's big. That takes huge energy for electrons, huge thermal energy for electrons to jump from the valence band to the conduction band. That's large energy. But look for silicon, it's only 1.12 electron volts. So even, at temperatures close to liquid nitrogen, which is 78 Kelvin, you can get a lot of free electrons in the conduction band. Even look at germanium, which is another semiconductor, you get 0.66 electron volts, even smaller. Gallium arsenide, which is a compound semiconductor, you get a band gap which is 1.42. Again, same thing with gallium phosphide, okay, and cadmium telluride, cadmium selenide, silicon, tin oxide. Now, these two are interesting. This is silicon nitride. Look at the band gap, 5. That's huge, that's big. That is why silicon nitride is an insulator. You cannot give electrons enough energy to go across the energy gap. Silicon dioxide, 9 electron volts. Even that's larger, much larger. Actually, this is the largest energy gap. So that is why silicon dioxide is the best insulator. So these two are insulator, right? This one too is an insulator. Okay, so here we need, these are insulated. All the others are semiconductors. Okay, now this is a problem which we will try to look at before we close this part, right? And that problem is E versus K. Remember the E versus K plot that I showed you when we solved Schrodinger equation? you get E versus K plot, which are continuous energy bands separated by forbidden energy gaps. Let's assume that we solved Schrodinger equation for some U, potential U, and let's assume that we found a functional dependence of E versus K. So E versus K is given as E equals 2.8 minus A cosine K A, where E is in electron volts. And the constant capital A is 1.7. The constant is small a is 2 times 10 to minus 8 centimeter. And K is in the range minus pi over A to plus pi over A. So let me just go back quickly here and remind you what we're talking about. This is the energy bands that we obtained. So let us look at this band here. Okay, it goes from minus pi by A to plus pi by A, and it's like this curve. So let's assume that we're able to write the equation of this curve in the range K minus pi A to plus pi A. And that's exactly what this talks about. So what you have is this equation for E versus K with these constants. Find the maximum and minimum energies and the corresponding values of K for this band, and also find the width in electron volts of this band. Now, again, going back, the question is, what is this maximum energy, which I call E1 here, and what's the minimum energy, which happens to be 0 here? What are these energies? And then from these, top and bottom, E1 and E0, get the energy band width. So that's the question that we're asked here. And that is very straightforward. It's actually a little bit of calculus, not more. So what we do is, this is E as a function of K in the region minus pi by A to plus pi by A for K. So we differentiate E with respect to K, and we let that equal to 0 to get turning points, the points for maximum and minimum. That is how you get it in calculus. You just differentiate with respect to the variable, which is K. So if we differentiate, the derivative of 2.8 is 0, the derivative of cosine is minus sine, and then you get A and you get a small a and capital A. So this is the derivative, and you set it equal to 0. So for this to be equal to 0, the sine should be 0, sine k should be 0, because I know capital A is not 0 and small a is not 0. They have values that are given up there in top. So this is satisfied when k is equal to 0, when the sine k equals 0, meaning k is equal to 0, or k is equal to plus or minus pi by a. That is within the range k from minus pi by a to plus pi by a. So these are the the turning points. We have 3 turning points: k equals 0, k equal to plus pi over a, or k equal to minus pi over a. Because in the case of k equals 0, we have sine 0 equals 0. In the case of k equals pi by a, we have sine pi equals 0, and sine minus pi is equal to 0 also. Okay, now to determine whether we have maximum or minimum energy values, we have to do the second derivative now. So we do d squared e by dk squared, and we substitute the values. For k equals 0, we get cosine 0 equals 1, therefore we get a squared a, which when we substitute for small a and capital A, we get that larger than 0. So if you get the second derivative at that point larger than 0 or positive, then that should be a minimum. So k equals 0 is minimum point for the function. And then if we substitute plus pi for plus pi over a or minus pi over a, we get cosine pi, which is minus 1. So we get minus small a squared, capital A, which is less than 0. So we get negative. So at plus pi over A or minus pi over A, we get a maximum point. So now we have determined our minimum and maximum points for K. So we substitute K equals 0 back, right? Here, we substitute K equals 0 to get the minimum or the minimum point, and that becomes 2.8, 1.7 cosine 0, which becomes 1.1 electron volts. And then we substitute K equals plus pi over A or minus pi over A to find our maximum energy. So we get E max equal 2.8 minus 1.7 cosine plus or minus pi over A times A, which is cosine pi. And it is an even function for cosine pi or cosine minus pi, we get minus 1 in both cases. So that gives us 4.5 electron volts for the maximum. And the energy width of the band is E max minus E min, which becomes 3.4 electron volts. So that's the solution of our band for this special solid. I think we will stop here and continue uh, uh, after a break of 10 minutes or so. So we'll stop here.